In my talk today, I would like to talk about the RASER, or to be more precise, about the multimode case of the para-hydrogen fueled RASER, because that one can either have high precision measurements in NMR, but you could also be observing complete chaos. And more people are actually getting RASERs, and people are even writing me or other people who have RASERs like, what is this? Can I get rid of this? What does this do? Why am I seeing this? And the reason for that is their FIB is just getting so good. SAPE is getting so good. We have so much polarization that we are just seeing this without not wanting it at some point. But to those who don't really know what I'm talking about, I would like to briefly repeat what I mean when I say RASER. So I mean radio wave amplification by stimulated emission of radiation. Some people call this a Zeeman maser. And it's pretty analog to a laser. So as in a laser, you have your optical resonator, you have your pumping with light, and then you generate a population inversion of energy levels, and then you have coherent emission of radiation. And you can do the exact same thing. For example, if you pump with para-hydrogen or with SABRE or even with DNP or something like that, you generate a population inversion on your nuclear spin states, and then you have an electromagnetic resonator around it. And that's now detecting your signal and works similar to the optical resonator. But the main difference here is that in contrast to a laser, where the slowest order parameter is the lifetime of a photon in the resonator, now the slowest order parameters are our nuclear spin states, so we can actually measure nuclear states with the precision of a laser, if you wish, and that can be really exciting. But to even get there, you need to surpass the RASER threshold, so you have to have enough polarization to get the coherent emission of radiation. And for that, either you have enough polarization, or your system is good enough, you have high homogeneity or high quality factor of your carrier, or just enough spins in your sensitive volume if you polarize big things, and so on and so forth. And if you've surpassed that, then instead of an FID, which is pretty short, then you have a continuously ongoing signal pretty much indefinitely. I hope one day I can share with John a setup where we can measure this for days, because also for the RASER, this is absolutely awesome. So that very much refers to the last talk. Of course, we also have problems with methanol evaporation if we measure for days and not only hours, but that's a totally different story. So in the beginning, you have the initial relaxation oscillations. Now they take a lot longer than for a laser, where it's in the order of milliseconds, because relaxation is so slow here and pumping is so slow. But essentially the same thing. And at some point you get into a steady state. And Stefan Appelt figured out the theory behind this, and we together published all this in 2020 in the PNMRS. And this is just the adiabatic approximation of the equations each individual mode goes through. And I talked about this extensively on Euroma. And when I mean adiabatic approximation, I mean getting rid of the initial relaxation oscillations in the beginning and just looking at what happens later on, where you only see your individual modes. But today's talk, I would like to dedicate to what can you actually see in different modes? What if you have multiple modes? What are you expecting? What can happen between those modes if you look at those equations and if you match that with experiments? So the first thing that can happen is the most boring case. You only have a singular mode, because all the modes you have are so close to one another that they just collapse on or renormalize into a single line. You can see mode locking, which is essentially self-organized mode locking, not active mode locking, but then you also see a frequency comp there. You can have the typical NMR case that I've introduced in the beginning, that you just see your NMR modes where they're supposed to be, if you wish. You can have intermittence, meaning at different points in time, different modes are most prominent. And finally, you can have so many period doubling processes that you eventually get chaos. That's, of course, absolutely not helpful for your NMR measurements if you have all the frequencies in there at the same time. But one day, maybe chaos can have other applications, and someone will use this for, I don't know, a true random generator or whatever. But today I would like to walk you through these situations and when do you get what, looking at the equations and trying to simplify that a little bit more. So the first case, if your renormalization width is larger than half the frequency difference, your lines collapse. You can simulate that. And right at the threshold, your renormalization width is essentially your your line width, but if you get higher polarizations, that gets a bit broader. So we checked that. We used 3-picoline, has a CH3 group, aliphatic, has aromatic rings. If you measure at 1 millitesla, so really low field, that's only 0.2 hertz apart, and 0.2 hertz is pretty close, and that collapses. On the bottom left, I've shown a simulation of like really narrow line width, how this would look like, that spectrum, if you could measure it in that way. But that's because of strong coupling regime, you have so many peaks there, but essentially even you can drive the polarization as high as you want, you will never even get 2 peaks, which you should be getting at some point, which are the 2 highest modes here. So that always stays a single mode case. But if you now use the exact same condition and measure that at 4 millitesla, you already have enough distance between those modes that you can see both modes, but they're strongly interacting with one another though, because they're still pretty close. So that's when you get a frequency comp. This is a measurement for it. The simulation looks pretty much the same. Modes are still fairly close, but not below that threshold. So you get what we call a odd frequency comp, which is self-organized. The pulses are ginormous in the time domain. If you see something like that, then you know you have modes that are very close to one another. And now if you move the modes even further apart, and I'm going to show first simulations of that. If the modes are far enough apart, you just get the exact frequencies out that you have put into your NMR spectrum. In the bottom right, you have the FID for this. Of course, it's not decaying because there is no decay. It's continuously being pumped by Saber, so you're getting signal all the time. And I think some people know this already. Like we used this in 2017 to write a beautiful Nature Physics paper where we brought more and more modes over the threshold, identified the states. Some of them, for example, this one, we measured for 1,000 seconds. I hope we can do more one day. We could do more, we could already do more. But in this example, you then get very, very narrow lines and do beautiful NMR with this. Or like extract NMR parameters, I should say. And more papers have come out that use this approach. But sometimes you're not doing experiments yourself. Sometimes people just come to you and ask, like, shall we work on this? Shall we work together? So the group from Ed Shekmanov and Baptiste Roland approached us and were like, yeah, we're doing FIP. What about using FIP for this? Why always Saber? Well, with FIP, you start with a very high population inversion, but that just decays because you're not continuously pumping. So you're getting into a situation where over time, your signal will be gone and you will not be measuring indefinitely. But you can have really funny effects, for example, intermittence. So as time is relevant now, on the bottom right, you can see the reaction. So vinyl acetate to ethyl acetate has a J coupling of 7 hertz, has a chemical shift of 2.7 ppm. They did this in a permanent magnet and spin off, so 167 hertz difference between those modes. They were able to determine those very precisely. But in some experiments, it looked kind of odd. So at the beginning, you have both modes at the same time, which you can here see a zoom of the time domain where the modes alternate between who's going to talk today. And then there's big bursts of, if you just look at the Fourier transform at the bottom, that can confirm that these bursts always belong to one of the modes being active or showing a RASER burst until all the polarization eventually dies out because there's no more polarization left. And we thought, what if we have even more polarization? And there were situations in there where right at the beginning, if you would Fourier transform, you would just get everything. And obviously, as you already know by the title of my talk, this is chaos because you have all the frequencies in there. If you simulate that, you get something that looks pretty similar. Doesn't look exactly the same because the simulation here only accounts for the 2 modes with a 7 hertz different, and the actual spin system of vinyl acetate is a little bit more complicated. But looking at the Fourier transform, you get something that's very similar. And now if you instead of look at no pumping, the no pumping case, but if you would be continuously pumping at exactly these conditions, actually, instead of having only the 2 modes, which you have with low polarizations, at exactly this polarization, you see a lot of lines in between essentially all the frequencies. You can still see the dominant ones in this case. I mean, you have to shift a little bit back and forth between those, but also like the time domain looks really funky and really chaotic. So that is a chaotic region. And we did not see that. And we thought like, why is this because higher polarization at some point always gives chaos? Haven't we checked that in simulations? Absolutely not. After this, we did a lot more simulations, and the regions where you see chaos are actually really slim. So randomly stumbling onto them is not a thing. It just happened because if you're a FIP, and then you go essentially through all the different polarizations. To explain this graph in a little more detail, is here in the bottom you have the equilibrium polarization as a population inversion d0. You could call this axis your polarization, where over here you have like a promille, and on this axis you have the frequency separation that you're actually measuring in your spectrum. So this is the 7 Hertz case here at the top, so 7 Hertz, 7 Hertz, 7 Hertz. Now this is the actual simulation for the case that we've seen before, and then at some point here you see chaos. And then after that, the polarization gets so high that there's nonlinear shifting of the modes. And if you simulate modes that are closer to one another and have a stronger nonlinear coupling, for example, here you can see right before the chaos, which you can actually also see here right after it, you already have the first 3 period doubling processes happening right before you go into the chaotic regime. As you can see, there's these small peaks between the main actual peaks of the modes. So, and with that, I would like to summarize the few little nice things that you can see in a RASER. You can either have the renormalized mode, so that's only the boring one mode. You can have mode locking. You can measure your beautiful NMR spectrum. You can have funky things like intermittence, where sometimes it's the one mode you're seeing, sometimes it's the other mode you're seeing, and you can see absolute chaos, whose applications are yet to be seen. But the easy thing is, if you know your polarization, if you know the distance between your modes, if you know how your pumping is, you can pretty much predict what you're going to get. And you can also, in the other way around, identify what's going on and what's happening. And you can simulate and understand these situations. And with that, I would like to thank all the team that has been working on this in the past, and my lab, who has always been supportive, and the opportunity to, during the COVID chaos pandemic, to work on actual chaos and have a lot of fun with that. Thank you so much.
Awesome talk, Sören. Thank you so much for sharing with us about all the different craziness that can go on with a RASER, or chaos, should I say. I guess John has a couple questions that he put. The first question is about the frequency comb. So he was wondering, is it a frequency comb or is it a signal with amplitude modulation? How do you, I guess, tell the difference?
It is a frequency comb. If you only have a signal with amplitude modulation, you would not see it in that way. You see that in the simulations. And you see that only by varying the distance between the two modes. You will see that if the modes get closer to one another, you'll get the frequency comb or the self-organized mode locking. And if you get even closer, they will collapse. And if you put the lines further apart, you will not see that. And also you can, in the simulations, make sure that there is no oscillation. But yes, of course, in this time domain, you'll see that actually your amplitude is modulating. So yes and no.
And I guess John's other question was, could it be advantageous to simply time pulses based on the FID rather than relying on radiation damping?
I would say no, because you want to be continuously acquiring for thousands and thousands of seconds. Why would you want to time pulses? Maybe I don't understand the question, but if you pulse in the middle of the RASER, you will just get something pretty random, because you will just read out or you will just flip 90 degrees the current Z magnetization or whatever. Yeah, maybe I don't understand the question, but
I'm using my unmuting powers. So say you didn't have inverted magnetization. So you arrange it such that you did not. Could you just have an FID and then pulse in phase with your FID and thus continually excite?
So whenever you excite, you perturb the system. So yes, you can do that. But you would need to have something that is continuous and not like changing with time. The most simple case with a 180-degree pulse obviously works, right? You hit your sample with a 180 and you get a RASER burst, and then everything, all your signal is dead. So you could do all this without hyperpolarization, just with a 180-degree pulse, right? And people have done that if they have a high Q resonator or whatever. But I'm not an expert on pulse sequences, and I don't know of a sequence which continuously would pump in that polarization in that way, and I would not know where the polarization would be coming from.